Let's jump right in. Welcome to this explainer, where we're going to take what might seem like a pretty dense chemistry topic and transform it into a really fascinating story. We're talking about how the entire inorganic world is literally built from the ground up. I mean, if you look around, the inorganic compounds that make up our planet are mostly found out in nature as silicates, carbonates, sulfides, and sulfates. But to truly wrap our heads around these complex materials, we actually have to go back to the basics. So, we're going to explore a comprehensive, super approachable overview of oxides, acids, bases, and salts.
Here's our roadmap for today. Number 1, we'll meet the inorganic family. 2, oxides, the oxygen combinations. 3, acids, the proton donors. 4, bases, the hydroxide producers. 5, salts, the neutral compromise. And finally, 6, properties and plant nutrients. Let's dive in.
Section 1. Meet the inorganic family.
Okay, so everything in the inorganic world can basically be categorized into 4 interconnected families. First up, we have oxides, which are formed anytime oxygen pairs up with another element. Next to it, we've got acids, defined by their ability to release hydrogen ions. Then, the counterpart to acids, we have bases, which release hydroxide ions. And finally, we have salts, which are the direct result of what happens when acids and bases neutralize each other. Grasping this core relationship is absolutely crucial. It's the key to unlocking exactly how inorganic chemistry operates.
Section 2. Oxides, the oxygen combinations.
When oxygen combines with another element, whether it's a metal, a nonmetal, or a metalloid, it creates a binary compound called an oxide. And depending on what it binds with, it falls into one of 5 distinct classes. First, we have acidic oxides. These happen when oxygen combines with nonmetals like carbon dioxide or sulfur dioxide. Fun fact, they're actually called acid anhydrides because if you dissolve them in water, they literally turn into acids. On the flip side, we've got basic oxides. That's where oxygen binds with a metal like sodium oxide or magnesium oxide, forming an alkaline solution in water. Then there are neutral oxides like water or carbon monoxide, which just don't react with acids or bases at all. And finally, peroxides. This is where oxygen takes on a highly reactive -1 chemical state, featuring this really interesting oxygen-to-oxygen link.
Now, we also have amphoteric oxides, which are just super cool. They are the ultimate chemical chameleons because they can react with both acids and bases to form salt and water. A perfect example of this is aluminum oxide. If you introduce it to hydrochloric acid, it acts like a base. But if you introduce it to sodium hydroxide, which is a strong base, it suddenly switches gears and acts like an acid. Either way, both reactions ultimately yield a salt and water. Because of this exact capability, acidic, basic, and amphoteric oxides are often grouped together and called salt-forming oxides.
Section 3. Acids, the proton donors. So according to the Arrhenius definition, for a substance to be considered an acid, it must contain ionizable hydrogen that it can release into water. It essentially acts like a highly dedicated proton donor. This is exactly why lemons have that distinct puckering sour taste and why stomach acid can effortlessly break down your food. Whether we're talking about a binary acid with just 2 elements, like hydrochloric acid, or a ternary acid with 3, like sulfuric acid, they all share some remarkable properties. They taste sour, they dramatically change the color of chemical indicators, and they react with active metals to yield pure hydrogen gas. Plus, because they release these ions, aqueous solutions of acids conduct electrical currents. If an acid dissociates completely in water, it's a strong acid. If it only dissociates partially, you guessed it, we call it a weak acid.
Section 4. Bases, the hydroxide producers.
Now, there is a perfect, almost poetic symmetry here. Where acids are sour and donate hydrogen ions, bases are bitter, feel soapy like a literal bar of soap, and produce hydroxide ions. In chemistry, a base is usually an oxide or hydroxide of a metal. Sticking with Arrhenius, bases produce that OH- ion when they're dissolved in water. A classic example is sodium hydroxide. It's an ionic compound that simply releases its pre-existing ions right into the water. Interestingly, though, ammonia is also a base, even though it isn't an ionic compound itself. It actually reacts with the water to produce those critical hydroxide ions. And just like acids, strong bases ionize completely, while weak ones ionize only partially.
This really simple, elegant equation perfectly balances acids and bases. The pH measures acidic strength, while the pOH measures basic strength, and they always balance out on a scale up to 14. The general rule of thumb: the lower the pH number, the stronger the acid. It's a flawless balancing act that lets us understand just how potent an acidic or basic solution really is.
Section 5. Salts. The neutral compromise.
Think about this for a second. When you take a sour, active metal-eating acid that's just throwing off positive hydrogen protons, and you mix it with a bitter, soapy base that's releasing negative hydroxide ions, what do you think the result is going to be? They completely neutralize each other. They form water and a brand new ionic compound called a salt. The hydrogen and hydroxide perfectly combine to make the water. And what's left over, the metal from the base and the non-metal part of the acid, they literally join together. For instance, if you mix hydrochloric acid and sodium hydroxide, the sodium and the chlorine lock hands to form sodium chloride. Yep, that is everyday table salt.
But, this neutralization isn't always a perfect, clean brick. If the replacement of those hydrogen ions is 100% complete, we get a standard normal salt, like sodium chloride or potassium bromide. But if the replacement is only partial, leaving little pieces behind, we get an acidic salt, like potassium hydrogen sulfate. Conversely, if all the hydroxide ions in a base haven't been fully replaced by the acid's nonmetal parts, we get a basic salt. So the properties of any given salt are entirely dictated by the exact nature of the compromise between the acid and the base.
Section 6. Properties and plant nutrients.
Salts also have these totally fascinating relationships with atmospheric moisture. Hygroscopic salts absorb water right out of the air but stubbornly remain solid. Think of those little silica packets you find in a new pair of shoes. Deliquescent salts like calcium chloride go a step further. They absorb so much moisture they actually dissolve into a liquid solution. And then you have efflorescent salts, which do the exact opposite. They actually lose their internal water of crystallization back to the atmosphere.
Ultimately, these very inorganic compounds, these salts we've just created through this entire chemical cycle, serve as the essential macro and micronutrients that sustain all plant life. They act as nature's fertilizers. Macronutrients are needed by plants in large amounts, while micronutrients are needed in smaller, more precise doses. Whether it's through natural weathering or things like agricultural fertilizers, pesticides, and herbicides, the acids, bases, and salts we've explored today are quite literally the foundation of the global food chain.
As we wrap up this explainer, I want you to look outside. Consider how this endless cycle of oxides, acids, bases, and salts is quietly transforming the earth beneath our feet every single day. The exact same reactions we've broken down are happening right now in the soil, in the oceans, and inside the plants we rely on. So what hidden chemical compromises are happening in your own backyard right this second? Thanks so much for joining me on this deep dive into the inorganic family, and definitely keep questioning the science happening right in front of you.